So I mentioned when I was looking at the 2 by 2 determinant case that for future ones, we're essentially going to have our goal to be to get back down to that. So if we're looking at trying to compute a 3 by 3 determinant, we can start with a generic 3 by 3 matrix A, B, C, D, E, F, G, H, I. And what we're going to do is take that matrix and break it down into a series of smaller determinants to get the whole thing, using what's called expansion by minors, where if we have a matrix of this form, what we can do to get our minors is essentially look at eliminating rows and columns corresponding to specific elements in a specific row or column. That's the best way to go about this anyway. That is, if we want to take the minors for A, B, and C, what we would do is look at that matrix and go along the top column for A, B, and C and essentially remove the row and column corresponding to each piece's coordinate. So for A, we would be crossing out the top row along A and the first column down A's path to get the determinant EF HI or EI minus HF using the 2 by 2 determinant formula. Similarly for B, we would cross out the first row because that's where B lands, and the second column because that's B's column, position 1, 2 as it were, which would leave us with DF and GI in our determinant or DI minus GF. And then finally for C, we cross out the first row and the third column for position 1, 3, where C lands, to be left with DEGH, or with the determinant formula DH minus GE. And then from there, when we're taking each of these pieces, we have an associated value called a cofactor attached to them, where the cofactor is generated in terms of that element, and in particular, the coordinate of the element, where the cofactor for the element in position ij is given by -1 raised to the power I plus j. So in general, for 3 by 3 matrices, just as an aside, the cofactors will follow that pattern: 1, -1, 1, -1, 1, -1, 1, -1, 1, as that's the powers of -1, plus or minus 1, depending on whether the numbers are odd or even. But here, that leads us to our definition for the determinant of order 3, for that general form A, B, C, D, E, F, G, H, I. Along the first row, we would get A times -1 to the 1 plus 1 power times the determinant corresponding to that minor, EFHI, plus B times -1 to the 1 plus 2 power multiplied by that minor determinant DFGI, and then plus C times -1 to the 1 plus 3 times that determinant DEGH, which you can simplify down to A times EI minus HF minus B times DI minus GF plus C times DH minus GE. And actually, you can take this approach to get a general formula for a 3 by 3 determinant, but truth be told, and you can do this with any combination for row or column, but it's really not a clean formula to think about. And when it comes to these, really what you want to focus on are those values A, B, and C in the construction. Because if you have the right values for a row or column, you're going to see that a lot of those terms will simplify out. And that's really the game here, is being able to recognize which row or column in a 3 by 3 matrix is the best candidate to expand your minors around. That is the one that will make your terms the nicest that we can hope for. Where sometimes it's not so much obvious, but there is definitely a best candidate. And that's what we'll see next, is how we can look at computing one of these 3x3 determinants specifically, where hopefully we'll have a clear choice for what we want to work around.